For more than a century, the speed of light has stood like a wall at the edge of reality. According to Einstein's theory of relativity, nothing carrying information can travel faster than light through empty space. Not a spaceship, not a radio signal, not a message. Not even the fastest machinery humanity could ever build. That rule became one of the foundations of modern physics. It protected cause and effect. It kept the universe in order. If something could send information faster than light, then the future and the past can begin to blur in dangerous waves. A message might arrive before it was sent. An effect could appear before its cause. Reality itself would start to feel unstable. Then, quantum physics arrived and made everything uncomfortable. Deep inside the smallest parts of nature, particles behave in ways that seem to ignore distance. Two particles can become linked so deeply that measuring one appears to instantly tell us something about the other, even if they are separated by enormous distances. Einstein hated this idea. He called it spooky action at a distance. And the strange part is this: experiments show that quantum physics was right. Einstein's universe was strange, but it was still orderly. Space and time could bend. Gravity could wrap light. Clocks could run differently depending on speed and gravity. But even in this flexible universe, one rule remained firm. Light speed was the limit. Light travels at about 300,000 kilometers per second in a vacuum. That is almost impossible to imagine. A beam of light can circle Earth more than 7 times in 1 second. It takes light from the sun about 8 months to reach us. It takes years to cross the distance between nearby stars. But as fast as light is, the universe is even larger. Galaxies are millions and billions of light years away. If we send a message to a distant star, it may take years, centuries, or longer to arrive. That is not a flaw in our technology. It is built into the structure of reality. At least that is what relativity seemed to say. Then quantum mechanics revealed a deeper layer of nature, and that layer did not behave like ordinary reality at all. Quantum entanglement begins when two particles become part of the same quantum system. Once they are entangled, their properties are connected in a way that cannot be explained by thinking of them as two completely separate objects. Imagine two particles created together and then sent in opposite directions. One travels to a laboratory on Earth, the other travels far away. According to ordinary thinking, each particle should already have its own hidden properties, like sealed envelopes waiting to be opened. But quantum physics says something stranger. In many cases, the properties are not simply waiting there in a definite form. They become definite when measured. And when one particle is measured, the result is linked with the rest of the other. This is where the mystery begins. If the two particles are far apart, how does the second one know what happened to the first? Is something traveling between them? Is there a hidden signal moving faster than light? Or is nature simply not built in the way our minds expect? Einstein believed something must be missing. He thought quantum mechanics could not be the full story. In 1935, Einstein and two other physicists, Boris Podolsky and Nathan Rosen, presented a famous argument. Today, it is known as the EPR paradox. Their goal was not to prove that faster-than-light signals existed. Their goal was to show that quantum mechanics seemed incomplete. To Einstein, the idea that measuring one particle could instantly affect another distant particle was unacceptable. It appeared to violate locality. The idea that objects could only be influenced by their immediate surroundings. If something happens here, it should not instantly change something far away without anything passing between them. Einstein preferred the idea that the particles carried hidden instructions from the beginning. In that view, measuring one particle did not affect the other. It simply revealed information that was already there. For years, this debate seemed almost philosophical. Quantum mechanics worked incredibly well in experiments, but the question remained: was the universe truly strange, or were there hidden variables underneath the surface, making everything appear strange? In the 1960s, physicist John Bell developed a way to test the difference between Einstein's hidden variable idea and the predictions of quantum mechanics. Bell showed that if particles simply carried hidden instructions, their measurement results would follow certain limits. These limits became known as Bell inequalities. If experiments violated those inequalities, then the simple hidden variable explanation could not be right. That was the turning point. The argument was no longer just about interpretation. It could be tested in the real world. Over the following decades, physicists performed increasingly careful experiments with entangled particles. The results repeatedly supported quantum mechanics. The particles behaved as their connection was deeper than any normal local explanation could allow. This is why people say quantum physics broke the speed of light. Not because it lets us send a text message across the galaxy instantly, but because it reveals a connection in nature that does not fit comfortably inside our everyday idea of space and distance. The thing quantum physics breaks is not the speed limit for communication. It breaks our intuition. When two entangled particles are measured, the results can be correlated in a way that looks instant. But the result of each individual measurement is still random. You cannot control the outcome on one side to send a message to the other side. That detail is everything. If one scientist measures an entangled particle on Earth, the result may be linked to the result of another measurement far away. But the scientist cannot choose the result. Because the result is random, there is no usable signal. The other scientist cannot look at their particle and know what message was meant to be sent. Only later, when both scientists compare the results through normal communication, did the strange correlations become clear. And that normal communication still cannot travel faster than light. So quantum physics gives us something that feels faster than light, but not in the way science fiction wants. It gives us connection without communication, correlation without a message, mystery without a usable shortcut. Even when explained carefully, entanglement still feels impossible. It suggests that reality is not made of separate little objects, but fixed properties waiting to be discovered. At the quantum level, nature seems more relational, more connected, and more dependent on measurement than ordinary experience suggests. This is what makes quantum physics so disturbing. It does not simply say that the universe is complicated. It says that the familiar world may be built from something deeply unfamiliar. Particle can be in a superposition of possible states until measured. Two particles can share a single quantum description even across distance. Measurement can reveal correlations stronger than anything allowed by classical physics. And yet, the universe still prevents us from using this weirdness to break casualty. It allows entanglement but blocks faster than light messaging. It gives us spooky correlations but not a cosmic telephone. It is also as if reality opens a door just wide enough to show us something impossible, then closes it before we can step through. This also explains why quantum teleportation is often misunderstood. The name sounds like science fiction, as if matter can be instantly transported from one place to another. But quantum teleportation does not move a person or object instantly through space. Instead, it transfers the quantum state of a particle using entanglement and ordinary classical communication. The entanglement is necessary, but so is the classical message, and the message still obeys the speed of light. So even one of the strangest quantum technologies does not truly break Einstein's limit. It uses the rules of quantum mechanics in a way that seems magical, but it does not let information outrun light. That is the pattern again and again. Quantum physics challenges the way we think, but it does not let us cheat the universe. Even without faster-than-light communications, entanglement may change civilization. It is already central to quantum computing, quantum cryptography, and future quantum networks. These technologies may one day allow new kinds of secure communication, powerful simulations, and computing methods that would be impossible for ordinary machines. The irony is that the strangest part of physics may become one of the most useful. What once looked like a philosophical problem for Einstein is now becoming the foundation of real technology. But the deeper mystery remains. What does entanglement actually mean? Are particles connected through something beyond space? Is space-time itself emerging from quantum relationships? Is the universe at its foundational less like a machine and more like a network of information? Scientists do not fully agree. The experiments are clear, but the meaning is still debated. So, did quantum physics break the speed of light? Not in the simple way the phrase suggests. It did not give us faster than light travel. It did not give us instant messages across the universe. It did not destroy Einstein's rule that usable information cannot outrun light. But it did break something else. It broke the idea that the universe must behave the way common sense expects. It showed that particles separated by distance can share a connection so strange that Einstein himself struggled to accept it. It proved that reality at its deepest level is not built like the world we see around us. That speed of light still stands as the limit for messages, matter, and cause and effect. But quantum entanglement shows that beneath that limit, nature is doing something far stranger than ordinary motion through space. Maybe nothing truly travels faster than light. Maybe the terrifying truth is that at the quantum level, distance is not as real as we thought.